Let's see one more application of this principle of mutual exclusion inclusion, that is calculating derangements. So the problem of derangements is like this. Okay, I will tell that problem with some story. Okay, example, there are 5 people, and they are numbered first. Their numbers are 1, 2, 3, 4, 5, and they went to some movie, and these are the chairs, and they sat in some random chairs, but continuously, let's say. Then while watching the movie, they realize that their seats are not good. Everyone's seat is not good. Okay? So no one is satisfied. So what they wanted to do is, while watching the movie, everyone thought this one, same thing, that once the break comes, we'll go out, and when we come back, we sit in different seat. That is what everyone planned. Okay. So if really they work it out, because everyone is happy changing their seats, right? So what if they go back? When they go to some fresh rooms, and if they come back, and initially their seating positions are 1, 2, 3, 4, 5. Then if one takes 2's position, okay, that means here 2 takes 1's position, 3 takes 4 position, let's say 5 takes 3's position, in that way. 2, 1, 5, 3, 4. Is it not derangement? Derangement is nothing but changing everyone in the group changing their positions. That's it. That means for this arrangement, so no element in the previous position, you see. 2 is in different position, 1 is in different position, 5 is different, 3 is different, 4 is different. This is one of the derangement. Okay. Now, is there any other derangement? Please think about it. Let me write one more derangement, that is 2, 1, up now I am successful, 3, no problem, 4 here, 5 here. Is it okay? We'll see. But don't compare these values with these positions. Okay, this is one of the derangement. So this is what our initial arrangement. With this arrangement we should figure it out. Okay, 1 versus 2 different, 2, 5 different, 3, 1 different, 4, 3 different, 5, 4 different. That's why this is one more derangement, isn't it? In that way we can have lot of derangements for this arrangement 1, 2, 3, 4, 5. Understand? But these two derangements D1, D2 can have common positions. Okay, don't compare D1 and D2. We have to always compare with the first arrangement. Now one more derangement I can write like this, maybe 3, 4, 1, 5, 2. Yes, 3 different position, 1 versus 3, 2 versus 4, 3 versus 1, 4 versus 5, 5 versus 2. Yes. So everyone is in different position, right? So these are all derangements. Now the question is, how many such derangements possible? That's it. Okay. So we are going to figure out a formula for it. So here I want to say that it's an application of principle of mutual exclusion inclusion. Why I will tell you. I give you one pattern. You tell me whether it is derangement or not for 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5 here. Okay. 1, 3, 2, 5, 4. So this is not derangement. Think about it. Why? Since 1 is in the correct position, isn't it? Very good. Try this one. 2, and you don't know remaining positions. How are I arranged? But whatever the way I arrange the remaining positions, definitely this is not derangement, isn't it? Because 2 is in the correct position. So in that way, any non-derangement is easy to identify, isn't it? I will show you. There are 5 structures, so each non-derangement falls under that structure, you see. Either your non-derangement will be either in this model, or in this model, or in this model, or in this model, or in this model, isn't it? You cannot have another model, right? So finally, all non-derangements can be, happily divided into 5 parts, okay? So let me use a set form to represent them. So I am calculating non-derangements. Okay. So now the question is, how many derangements possible for 5 numbers? Given 5 numbers, how many derangements possible? First I calculate non-derangements. Okay. Let me denote non-derangements like this. all the non-derangements are, because 1 is in the correct position, let's say that is S1 set, or 2 is in the correct position, or 3 is in the correct position, or 4 or 5. Okay. So I want to calculate S1 union S2 union S3 union S4 union S5. For understanding it clearly, try to understand S1. Write the description of S1. S1 is nothing but, all non-derangements. They are all non-derangements where 1 is in correct position. That's the reason it is non-derangement, correct position. What about 2, 3, 4, 5? I do not know. I only know that 1 is in the correct position. Okay, but I don't know about 2, 3, 4, 5. So that is S1 set. Similarly, you can define S2, S3, S4, S5 exactly like this. Now, all non-derangements are definitely either S1 union S2 union S3 union S4 union S5. We have to compute non-derangements first. Why, sir? If it is easy to compute, we can apply principle of mutual exclusion inclusion for that. Once you do it, then we can go for derangements. According to the formula, it's a very big formula, isn't it? So don't write it. I will tell you a shortcut. We know the formula. It is nothing but in the high level, sigma all the individual sets S1, S2, S3, S4, S5 minus sigma all size 2 intersections, right? That means all 2 intersections, S1 intersection S2, S1 intersection S3. Rather than writing the formula, we first calculate the values. First we calculate value of S1. Okay, so I will tell you the reason for it. What is value of S1? First, what is description of S1? All non-derangements where 1 is in the correct position. How to form one arrangement where 1 is in the correct position? Very easy. Fix 1 here and only change these 4 positions, right? So 4 positions. What are the other elements we have? 2, 3, 4, 5. Take this 2, 3, 4, 5 and arrange them in these 4 positions. Whatever the way you do, that will be non-derangement of this case, isn't it? So that's 5. How many ways you can arrange 2, 3, 4, 5? 4 objects into 4 places. It is template number 2 or 3, I don't remember. It will be 4 factorial, we know that, right? So arranging 4 objects, which are different objects, into 4 different positions can be done in 4 factorial ways. 4p4, formula is npr. Here n is 4, r is 4. 4p4 is 4 factorial. Now similarly S2 value, right? Mod S2 also same 4 factorial, because problem is same. What is S2? How many non-derangements possible where 2 is in the correct position? So 2 is in the correct position, then what about these 4 positions? You can arrange in any way, then there are 4 factorial ways. So you realize that finally mod S1, mod S2, mod S3, mod S4, mod S5 are same. Remember it, all are 4 factorials. Then we have to compute this intersection, 2 intersections. Let's compute 2 intersections, okay? That is S1 intersection S2. First describe it. These are all patterns versus patterns, common patterns. These are all patterns where 1 is in the correct position. These are all patterns where 2 is in the correct position. Then common patterns are where 1 is in the correct position, 2 is in the correct position. Then only these 3 positions can be varied with 3 positions. Remaining 3 numbers 3, 4, 5 should be arranged here. Isn't it? So how many ways you can arrange that 3, 4, 5 into 3 positions? Obviously 3 factorial. In the same way, S2 intersection S3, everything is 3 factorial, you remember. So that's why I computed only S1 intersection S2, but all 2 intersections are 3 factorial. Let's go to 3 size set, that means 3 intersection. That is S1 intersection, S2 intersection, S3. What is the answer for this one? So description is, this is a derangement, non-derangement where 1 is in the correct position, 2 is in the correct position, 3 is in the correct position. That's why it is common in 1 and 2 and 3. That's why it will be 1, 2, 3 followed by these remaining 2 positions can be varied 2 factorial ways. By this time you can understand that, isn't it? Similarly, any 3 intersection will be like this and it will have 2 factorial arrangements. Okay. Now we will go to size 4, that means 4 intersection combinations. One of them is S1 intersection, S2 intersection, S3 intersection, S4, right? That is nothing but it is a non-derangement where 1 is in the correct position, 2 and 3, 4, everything is in the correct position, 1, 2, 3, 4. But the only one object which is 5, we don't know. But of course there is only one other position, then one way we can arrange. That means you have one element, one position, one factor ways we can arrange. In the same way, let's go to 5 size intersection. That means, intersection with 5 sets. S1 intersection, S2 intersection, S4 intersection, S5. That is 0 factorial, which is of course 1. How many arrangements possible where 1, 2, 3, 4, 5 all are in the correct positions? Yes, 1 is possible, right? Right, 1, 2, 3, 4, 5. So only 1. That is 0 factorial. Okay. So using these values, we can simplify this formula. Let's do that. Okay. First of all, we write a formula. Formula is like this: sigma all Si, isn't it? Next, minus sigma all size 2, Si intersection Sj, plus sigma all 3 size, Si intersection, Sj intersection, Sk, so on, right? And we know the formula, we directly write the values. But this sigma, we have to add all that S1, S2, S3. How many such sets are there? 5. One is S1, second S2, S3, S4, S5, right? So there are 5 such sets. Each one's value was 4 factorial. Did you remember that? Yes, minus. Now this one is critical. What is it? How many 2 size intersections possible? That means how many? These are all combinations, you see. We have S1 intersection S2. We have S1 intersection S3. By observing the intersections, you can realize that, do we have S2 intersection S1? No, we have only one for S1 intersection S2 and S2 intersection S1. That means it's not arrangement. It's like a combination of 2 sets. How many 2 combinations possible out of 5 sets? 5C2. It's a selection problem. Out of 5 sets, if you take any 2 sets, that will form this combination. So that's why there are 5C2 combinations, isn't it? And each combination's value we have computed, which is 3 factorial. Understand? Now plus. To understand it very clearly, I will tell you, one more interpretation. That is, example, Si intersection Sj intersection Sk. Let's call 1, 2, 3, 4, 5 as teachers. Okay. Then each this size 3 intersection, or intersection of 3 sets is nothing but each set is a teacher. It's a combination of 3 teachers. How many combinations we can form with 3 teachers out of 5 teachers? Is it not 5C3? Yes, that's why there are 5C3 such combinations, and each combination's value we computed, which is 2 factorial. Now next time it will become that all size 4 intersections are 5C4 into 1 factorial plus 5C5 into 0 factorial. Okay, if you extend it, you get like this. So 5C5 is what? So this represents what? All the 5 size intersections. There is only one such intersection where there are 5 sets and its value is 0 factorial. Okay. Now this is a formula. If you simplify it, you get 76. Okay. So I am not simplifying, anyone can simplify it, isn't it? So that's why this, if you simplify, you get 76. But what's our question? What is this? This is all non-derangements, isn't it? Why they are non-derangements? Just recall, this is all the arrangements where 1 is in the correct position, or 2 is in the correct position, 3 is in the correct position, or 4 or 5 is in the correct position. That's why they are not derangements, right? So we calculated opposite set. Why you calculate non-derangements first? The reason, non-derangements are easy to calculate because they can be represented as union form, and we have a formula for only union form. That's a problem. That's why I calculated non-derangements. Then we'll come to derangements. So derangements are nothing but all arrangements minus non-derangements. If there are 5 objects, let's say Let me do here. If I have 5 objects, 1, 2, 3, 4, 5, how many arrangements possible? 5 factorial ways we can arrange them. Out of them, these 76 whatever you calculated are not derangements. Then if you remove them, remaining everything supposed to be derangements. That's why answer will be 44. So formula for derangements is total arrangements minus non-derangements, which you have just computed. Understand? So this is one more example of principle of mutual exclusion and inclusion. Okay. Let n equal to p square q. Let's see one numerical problem. N equal to p square q, where p and q are distinct prime numbers. Then how many numbers m satisfy 1 less than or equal to m less than or equal to n? That means how many numbers are between 1 to n has GCD of m comma n 1. So GCD means greatest common divisor. Between two numbers, greatest common divisor is 1, means the among the divisors of m comma n, greatest itself is 1. That means there is no number which is greater than 1 which is common divisor of m comma n. That means what? So there is no divisor, right, other than 1. Then definitely I can say that automatically there is no common prime factors, right? So between these two numbers there is no common prime factor. Example, if there is one common prime factor like 2 comma 2 for m comma n, then GCD will become minimum 2, right? Because one common divisor is 2, right? Then it might become 2. But we know that GCD is 1, then greatest common divisor, that means among all the divisors, greatest is 1. That means there is no other divisors. Then there is no common prime factor. So that's why GCD of m comma n 1 indicates that they are relatively prime numbers. Okay, only for relatively prime number it happens. Now with that, this question finally become how many numbers satisfy this GCD of m comma n 1. That means how many numbers are relatively prime numbers to n, right? Especially between 1 to n. We know the formula. How many numbers between 1 to n which are relatively prime numbers to n? For that formula is, we know that first of all we have to identify all the prime factors of n, because n equal to p square into q, where p and q are prime numbers. Then already factorization is given, right? The prime factors are p into q, isn't it? It's like 2 comma 3. Then question number 1, how many numbers which are divisible by p? So that will be, so the problem is like this. Now we have to find out. తిక్కుగా రావట్లేదంట. ఇది వేరే తీసుకున్నా, ఇంకోటి ఉంది రెడీగా. Yes. Now relatively prime numbers, if you want, then that will be total minus non-relatively prime numbers, right? Non-relatively prime numbers. But total numbers are n, isn't it? Minus the total non-relatively prime numbers just we have computed, that is pq plus p square minus p. We know that n is p square q. Then let's substitute it. P square q minus pq, minus plus minus p square, minus into minus plus p. Now let's simplify it. See, if I take q and p common, pq common, then I get p minus 1, isn't it? Minus, if I take minus common and p common, you get p minus 1, right? Now again I can take p minus 1 common. If I take p minus 1 common, then you get pq minus p, isn't it? So now pq minus p, in that if I take p common, you get q minus 1, and here p minus 1. So finally p into p minus 1 into q minus 1, p into p minus 1 into q minus 1. So this is a solution for this problem, but we can solve this problem in an easier way, that is substitution. So rather than doing all these things, what I do is, our question is n equal to p square q, right? This is n. Let's take p as 2. and q has one more prime number which is smaller generally, so that simplification will be easy for us. Then n is 2 square into 3, 12 kind of number, like 12, otherwise anything, like I can take 3 square into 5 something. Now question is, how many numbers between 1 to 12, 1 to n, which are relatively prime numbers to 12, right? Let's list out the number of the numbers which are relatively prime numbers to 12 between 1 to 12 is, first of all, 1. I will tell you why 1 is relatively prime number to 12. First, do the factorization of 12. 12 is 2 into 2 into 3. Of course, we know that, right? P square Q. Now, 1 doesn't have any prime number in it, right? 1 is not prime number. So, 2 is a prime number. Prime number start from 2. Okay. So, 1 is not prime number. So, 1 doesn't have any prime numbers in it. That's why there is no common prime factor. So, 1 and this number doesn't have any common prime factor. So 1 is right answer. Now next 2, no, because 2 and this 2 has a common, right? Next we can't take 3, we can't take 4 because 2 common. 5, I am listing out. 6, 2 and 3 common. 7, yes. 8, 2 common. 9, 3 common. 10, 2 common. 11, yes. 12 all common, right? So finally 1, 2, 3, 4. Answer supposed to be 4. Simply go to the options and substitute. Relatively prime numbers are 4, where p value 2 and q value 3, right? Let's substitute. If I substitute, you get 2 into, so q is 3 here, 3 minus 1, 2, 2 to the 4. Yeah, a also, a is showing answer, right? Like equal value, but don't tick it because the other options might, satisfy. We know that D is the correct answer, right? That's why. So that's why whenever answer matches, just don't tick it finally, keep a question mark. Now go to second option, 2 into 3, 6, wrong option. This one, 2 square 4, 4 minus 1 3 into q minus 1 2, 3 to the 6, wrong option. Now we have p into p minus 1, q minus 1, second one p into q minus 1. For that we have to go for another possibility. Let's take n value this time 2. Q value, let's say 5, then number will become 2 square into 5, 20. Now list out all the numbers between 1 to 20 which are relatively prime number to 20. Okay, same, let me list out. 1, yes. 2, no, 2 common. So you know that 2 should not be common, 5 should not be common. Then 3. Next, I am listing out quickly. 7, then 11, 13, 17. Then 19. These are all prime numbers, of course. 1, 2, 3, 4, 5, 6, 7. I got 7. So substitute now. Anything else? 1, 3, 5 is wrong. 7, then 9. No. Yes, 9 also, because nothing is common, right? Because there is no prime factor 3 in this one. So 1, 3, 9, 7, 11, 13, 17, 19. I got 8. Let's substitute. Then it will become 2 into 5 minus 1, 4, 8. This one also gives 8. The reason I will tell you. Whenever you take p as 2, then p and p into p minus 1 gives same answer. That's why for everything you are getting same answer. Then substitute n value 3. Sorry, p value 3 and q value, let's say 5. Then what happens, we'll see. Let's say p equal to 3, q equal to, let's say take 2, then it will become 3 square into 2, isn't it? So 9 into 2, 18. For this we try. So p is 3, q equal to 2. For 18, how many numbers between 1 to 18 are relatively prime numbers to 18? Then answer 1, then 5, 7, 11, 13 and 17, isn't it? 1, 2, 3, 4, 5, 6. When p value 3, q value 2, answer supposed to be 6. Substitute. P is 3 and q is 2. 2 minus 1, 1. 3 1 is 3. But if you come to option D, it will become 3 into 3 minus 1, 2 into q minus 1, 1. So 3 to the 6. Only option D matches. Right? In that way, using the substitution also we can answer this kind of questions. But we have to, substitute right values. Okay. Okay. So Let's discuss circular permutations. Let's discuss about circular permutations. Circular permutations are different from linear permutations. Okay, so why we'll see. Generally, circular permutations can be imagined like this, isn't it? Like this positions 1, 2, 3. Let's take some 5 positions. Okay, now this is circular arrangement, whereas linear arrangement is like this, right? You will have positions 1, 2, 3, 4, 5. The difference between this circular arrangement and linear is all these positions have distinct properties, like this is first position, this is second. In that way I can number them. But here when it comes to circular arrangement, there is no meaning to position, like it's not a position here. So you can't say this is first position. The reason, everything is a first position. How can you say that this is first one, right? You can't say that. Is it first? Is it first? No. There is no we can't distinguish it, isn't it? But here you can distinguish like first, second, third, fourth, fifth. That's why these arrangements or circular arrangements are different from linear arrangements. We know that if you have n objects, then we can arrange them in n factorial ways, isn't it? In linear arrangements. When it comes to circular, answer is not n factorial. We'll try to derive it. So what I do is, in circular arrangements, just observe some circular arrangements. Example 1, 2, 3, 4, 5. It is one circular arrangement, isn't it? Now, the corresponding linear arrangement for this one is, I try to decode this one as linear arrangement. Okay, so I start from here and I try to write them from here right to left. Like I start here and I try to list out them. Then you get one linear arrangement 1, 2, 3, 4, 5. Okay, now if I change this position, if I rotate this table, like if I write 5 here, that means I am rotating the table 5, 1, 2, 3, 4. Then in circular arrangements, this is same as previous one. There is no difference. Try to understand. So only you are changing the view. If you view from here, same arrangement, previous arrangement 1, 2, 3, 4, 5, from here you see 5, 1, 2, 3, 4. So that means 5, 1, 2, 3, 4 is not a new circular arrangement. It's just same arrangement, but you are changing your view, right? So but if you come to a linear arrangement, for this linear arrangement is 5, 1, 2, 3, 4. What I want to say is 1, 2, 3, 4, 5 has one circular arrangement. 5, 1, 2, 3, 4 has 5, 1, 2, 3, 4 has one circular arrangement. Both are same. Understand? Let's see the story about circular permutations. Circular permutations are different from linear permutations. The reason, in circular permutations, there is no importance to positions. Okay, but in linear permutations you have importance to positions. I will show you with an example. Example, you have 4 objects 1, 2, 3, 4. Then when you arrange them in a line in a linear way, so you give importance to positions. Like we say this is first position, this is second, third, in that way fourth, isn't it? But when it comes to circular permutations, like, so that means you are arranging them in circle. Then in these 4 circuits you tell me which one is first position, which one is second position. So it is impossible. But whereas in this linear arrangement, leftmost is first, rightmost is last, isn't it? But in this one you tell me what is leftmost, what is rightmost. You understand? That's why there is no such kind of differentiation. But here you have differentiation. That's why circular arrangements are different from linear arrangements. So we try to derive a formula for circular arrangements. Before that, we try to see one observation, like we try to list out some circular arrangements. Let's see picture number 1. In this picture number 1, you have one arrangement 1, 2, 3, 4. Okay. Now take the picture number 2. It looks a different arrangement, but I want to say that in circular arrangements, this and this are same. I will tell you why. So this, whatever the arrangement, imagine like 1, 2, 3, 4 are people. So these people, having some dinner or something in a circular table. Now, if I change my view, like there is no difference between these two. Why? Simply rotate the table. So example 1 is here, after that 2, after that 3, after that 4. Now where is 1 in this picture? 1, after that 2, after that 3, after that 4. So simply rotate this table, like if I rotate so that 1 comes to top like this, then you see that these two are same. There is no difference, combination wise they are same. Now see this picture number 3. If I rotate it one more time, then 4 comes here, 1 comes here, that means just I am rotating the table. So rotating the table is not a different configuration. So it's just my perception, my view. Rather than viewing from here, you view from here. Then if you rotate the table, then you are viewing in a different way, right? So example 1 comes here, just move the table like this. Then 1 comes here, 2 here, 3 here, 4 here. So it is again same thing, but your view is different. You are viewing from different angles, I can say. When you view from different angles, how can you say that they are different permutations? No, right? So that's why this one, this one, this one, this one. So this is again rotation of this one, slightly rotated. So the 2 comes here, 2, 3, 4, 1, right? So finally all these pictures are same with respect to circular arrangements. So try to rotate it again. So 1 reaches here, 2 here, 3 here, 4 here, and you realize that you get it again. Then if you repeat it, you get only these 4 combinations. So finally, these 4 combinations are only one arrangement in circular arrangements. But in linear arrangements, these 4 might be different. Okay, leave that part. So what I want to say is, so circular arrangements are somehow different from linear arrangements. You agree with respect to this concept? If you understand this concept, then easily I can derive formula for circular arrangements. How you see? Let's take one circular arrangement with some enough objects like 1, 2, 3, 4, 5, so many. Okay, don't mind the number of circles, but let's say the objects which I am arranging is 1, 2, 3, 4, 5, 6, 7, 8. Let's say 1, 2, 3, 4, 5, 6, 7, 8. I am going to arrange these 8 objects in the line. Then how in a circle? Then how many different ways I can arrange them? Okay. So first of all, what I do is I try to arrange, or otherwise I try to arrange in one way. Okay. I want to see one configuration. So you can see 1 here, maybe 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, 8 here. Isn't it? Okay. Now, what is my idea is just observe where is 1. Okay. Okay. Example 1 is here. With respect to 1, you try to solve the problem. Okay. Now you can see 1 here. So what if I can't see 1 here? There will be 1 somewhere, right? You rotate the table such a way that 1 comes to this point, so that it is easy to see. Okay. So otherwise, directly go to the position where there is 1. Okay. Now just locate that one. I am not doing anything. Just locate that point 1. Now, if there is 1 here, then what about these objects? These are all remaining 7 objects, isn't it? Okay. With respect to 1, if you see, these people are arranged, right? Now you see. With respect to 1, these 7 objects, their arrangements are not circular. They are actually linear. Why? You see. Now I can say that this is, with respect to 1 I am talking about, 2 is right side of 1, right? Rightmost. Okay, maybe. Then this is also, it is second object from right with respect to 1. This is third object from 1, which is at right side. Fourth object, fifth object, sixth object, seventh object. Now, once you fix 1, then remaining objects are linear. That means they have positions, right? They have numbers. That is what I want to say. Whereas in general circular arrangements, like here you see, there is no we can't distinguish the positions. But once I fix 1 here, these remaining positions can be distinguished. I am going to distinguish, see clearly. One's right but second position. In one's right it is third, in one's right's fourth, one's right's fifth, in that way. So all these positions are different. Writing 2, 3 is different from 3, 2. Why? Because in the previous arrangement 2 was immediately after 1. Now in this arrangement 2 is in the second position after 1. Right? So in that way, that's why now these positions automatically will become distinguishable. Whenever all the positions are distinguishable, they are like linear. Okay. Now what I want to say is, how many different ways you can arrange these 7 objects? Then that many circular arrangements. So how many ways you can arrange these 7? 7 factorial. That's why I want to say that the total number of circular arrangements are nothing but arrange only these 7 objects. You can't arrange one. Right? So some students argue, you taught only arrangements where 1 is in this position. What if 2 is in this position? So that will be covered by the previous argument. Okay? If 2 is in this position, you don't get a different permutation. Why? Because if 2 is in this position, 1 will be somewhere, isn't it? Then go to 1 and rotate the table. By rotating the table, you can get one configuration, right? Already that is computed. What I want to say is, if 1 is here, if you rotate the table, 1 comes here, then same combination already counted in 7 factorial. That's why you don't require to count the combinations where 2 is in this position, because they are all same. Like just it's your view. You are viewing from 2. Never you view from 2, because if you view from 1, whatever the combinations you get, they are the distinct ones. And if I change this position from 1 to 2, then whatever the combinations you get, they are not at all different. It's all about by just you are changing the view. Because of your view change, new combinations will not be created. That's what I want to say. Okay. So finally, the idea is, whenever you want to compute circular permutations, you view like this. That is, I am repeating it. So first of all, imagine where is 1, locate him. Now with respect to 1, if you see, just see the number of arrangements. That number of arrangements are nothing but these arrangements. How many objects we have remaining? 7. How many ways you can arrange them? 7 factorial ways. So these are all will become circular arrangements if you add 1 to them. Understand? Now if I extend it to n, then locate 1, then remaining objects are n minus 1. Then how many ways we can arrange that n minus 1 objects in a linear way? N minus 1 factorial. So that will be the answer. Understand? So this is about circular permutations. From now onwards, you remember, number of circular permutations are n minus 1 factorial if you have n objects. Okay. Let's see problems. How many ways 6 people can be arranged in a round table? That's obvious, right? So for circular permutation formula is n minus 1 factorial. You have 6 objects, then answer is 5 factorial, which is 120. So problem number 1 is over. See the problem number 2. How many ways 3 boys and 3 girls can be arranged in a round table so that no 2 girls are adjacent? So here the condition is no 2 girls are adjacent. Let's imagine, a circle first. Okay, so this is a circle. In that we have to arrange, because it's a round table, right? 3 boys and 3 girls should be arranged. But girls are, they should not be adjacent. For that, what I do is, to have that condition, I arrange boys first. I arrange boys in the table. Now there are 3 boys, right? Boy 1, boy 2, boy 3. First you arrange these boys in the line, in a circle. Then how many different ways you can arrange them? We know the circular permutations. So that will be 3 minus 1 factorial, you remember. So that means 2 factorial, which is 2. Now once you arrange them, our job is not over. In the remaining positions, wherever you get gaps, like you can see a gap here, you can see a gap here, you can see a gap here, isn't it? In these 3 gaps, we should arrange these 3 girls so that no 2 girls are adjacent, right? So to have that condition, definitely boy should be arranged first, isn't it? Now don't say that again I do circular arrangement, because it is not circular arrangement. Why? Once you fix B1, B2, B3 in some combination, then this position is not indistinguishable. It is distinguishable, because this is the position between B1, B3. This is a position between B1, B2. This is a position between B3, B2. That means every position has a meaning now. Whereas if you have just three positions like this, initially, then these three are indistinguishable. That means you can't separate them or you can't distinguish them. But once you fix the boys, then the positions in between them will get distinctness, right? This is different from this is different from this. Then automatically it is like a linear arrangement. How many linear arrangements possible? For three objects, then it will be 3 factorial. That's why 3 girls can be arranged in 3 factorial ways. So 3 factorial ways. So finally, according to product rule, the total number of phase of arrangements of boys into arrangements of girls, it will become 2 into 3 factorial, which is nothing but 12. So answer for this one is 12. Okay, not 4.